All right, scholars, so today we're going to continue talking about circular motion with centripetal force. So centripetal comes from the Greek for center seeking. So there's a different type of force which we'll talk about called centrifugal force, which we'll talk about. It doesn't really exist. That is a center fleeing, centrifugal, center fleeing. Centripetal means center seeking in Greek. So the context in which we want to talk about centripetal force, I'm going to try to demonstrate here. I've got my keys on the end of my lanyard. You're not going to see it completely. It's going to go in and out of frame. But what we want to be able to analyze is what's like the tension, for example, on my lanyard, or if you imagine a ball on a string, what's the tension on that string? The engineering application would be, how fast can I swing this before it'll break the string and fly off at some angle or some direction tangent to the circle? And that's what we want to address today with looking at centripetal force. So I'm going to take my drawing implement for circles and draw a fairly detailed diagram, and then we'll take a look at it. So here I've added quite a bit. What we've got, we'll just imagine a ball swinging in a vertical circle of radius r. It's tied to a string, and we're going to assume, just for sake of argument here, that the velocity is constant the whole time, which is fair enough. So I've got my diagram here. If you need to pause and sketch it out, that's fine. What I've got is the object at different locations in its path. So here, just to the right, it's v1. And what I tried to do was keep the magnitude of each of these the same, showing that the velocity, the magnitude of the velocity is constant, or the length of these vectors is constant. So the implication there, and we've discussed this already, is that the speed is the same at each of these locations. The only thing that's changed is the direction. So since each one of these velocity vectors has the same magnitude or length, we can just call the velocity lowercase v, or really here we're just talking about the speed at any given moment. I've only drawn it in 3 locations, but it could really be any. So I've made a note here, which we got from our notes before on centripetal acceleration. Remember, I've said that it's a center-seeking force, or that centripetal means always inward. So the ball, if it's going in a circle, by definition, it's going to experience a centripetal acceleration always directed towards the center of the circle. The magnitude of that is going to be the same over and over and over again, because as we saw, the acceleration just depends on the speed and the radius. Those are all staying consistent. I should add here, this is the radius r. That means that the acceleration, the magnitude at least, is going to always be the same. And when we talk about centripetal acceleration, that's all we care about, is the number, and that we know that it's inward. So what we're going to do is we're going to work this into a couple of different ways that we can write centripetal acceleration. I already gave you one in the last set of notes, but here is another way that you can do it. So centripetal acceleration is v squared over r. Again, that was just in the notes we had last time. If you remember that v equals omega r, we can also substitute in, instead of v, we can substitute omega r. That's the angular speed times the radius of the circle. Remember here, we're assuming that the angular speed is constant. So this would just be plugging in v omega r all squared over r. So if we do a cancellation, we've got 2 r's, an r squared on top and an r on the bottom. We end up with our definition for centripetal acceleration, just extending our definition from last set of notes. We have v squared over r. That's what we already knew. And we have omega squared. We just square that and then cancel an r. We get the centripetal acceleration. 2 different ways to write it. So we've kind of rehashed centripetal acceleration, and now we want to go about defining centripetal force. The easiest way to do that is to just start with Newton's second law, which we're going to do in a kind of a special way. So we want the, we'll go like this, the sum of the forces. Instead of F net, we'll write it as the sum. That Greek letter just means add up all the forces. And I'm going to do that so that I can put a little subscript. We want to know the sum of the forces on something moving in a circle, and that's just going to equal mass times the acceleration. But here we've got a special acceleration since we're moving in a circle. I just wanted to give context because I know we haven't used this sum very much. It's the same as what we did with the second law. F net centripetal is what we're trying to say, is equal to ma centripetal. So the thing is moving in a circle. That's when we're going to use this formulation. So what does it look like to substitute in centripetal acceleration? Well, we've noticed that we can do that in two ways. So we could first write the sum of the forces on something moving in a circle, the centripetal force, is equal to m, and then a is v squared over r, where v squared over r is a centripetal acceleration. Or we could write it m times a, where we write a omega squared r. So that would be m omega squared r. So those are the different ways that we can write centripetal force. So I want to give you some context for what this means. The centripetal force is going to be whatever forces act together to make the thing go in a circle. So as an example, here we've got tension acting inward to keep this moving in a circle. We can call that T1. And the weight force of this thing would be acting straight down. So we would ignore it. It's not helping this thing move in a circle. Up at the top of the circle, remember this is a vertical circle, if we were going to actually work this out, the tension in the circle plus the weight of the ball would help keep the thing in a circle. We'll see this more as we move forward. And then at the bottom it would be a little bit different. The tension would actually need to be a little bit bigger, we'll call that T3, because it's fighting against the weight force of the ball pulling it out of a circle. So we're going to do plenty of examples where we use centripetal force, but the important thing is that it's the sum of all of the things making it move in a circle, all of the forces making our object move in the circle. So the last thing we're going to do at the bottom here is I'm going to write out an important conceptual note. I'll do that in two parts. So our first conceptual note is, as I kind of just mentioned, the centripetal force equation is saying find the sum, that's on the left-hand side, of the forces, it's on the left-hand side, acting on a body moving in a circle. And when you do that, it will let you figure out interesting things like how strong should I build this roller coaster, can I spin this thing this fast and not break this lanyard, and so on and so forth. I'm going to now write down the second important conceptual note. So the second conceptual note is that the centripetal force is not a new force, like gravity is a force, electromagnetism is a force, the strong and weak nuclear forces. Those are actual forces of nature. The centripetal force is not that, to be very clear. Instead, and I'm going to move my face so you can see it, the centripetal force is the sum of the forces which cause an object to move in a circle. And all you do is plug that in to the left-hand side. So we're going to do plenty of examples. This is just the beginning. I promise as we do more examples, it will make much, much more sense. Thank you, scholars. I hope you have a great day.